Okay, so last time we were talking about the 1,2,1,4 reactions. Pretty simple. You can just guess by the name what the product is going to be. Remember, in carbon 1, we always end up with some sort of hydrogen that came from our acid. And then on carbon 2 or 4, that's where we add our halogen. Okay. So we went through the mechanism. We know that it's an addition reaction, so we get rid of that pi bond. And remember, we always start counting from the less sterically hindered double bond. So that's why this one was carbon 1. After the attack, we're left with a carbocation. Remember, wherever that carbocation is, that's going to be where you add that bromine in that case. So it was really good to go to get the 1,2 product. But remember that to get to the 1,4 product, we needed to do some resonance. Okay, that's how we were able to move that carbocation into the 4th carbon. So that's how we got the 1,4 product. So very quickly, do we have any questions on the actual mechanism? Very good. Okay. So in this case, your professor is not only going to be asking about 1,2 and 1,4 products. He's going to be asking about the thermal and the kinetic product. So let's start with the kinetic product. It's the easiest one. How do we think we're going to find it? No idea? Kinetic sounds familiar in a way from general chemistry, maybe? A little? What do you say? What do you say that again? Yes, in a way, yes. So remember that kinetics in general is talking about the rate, the speed of the reactions. So in this case, to find the kinetic product for this one, it's always going to be the one that forms the fastest, which in this case, it's always going to be the 1,2 product, unless your professor states otherwise. Sometimes he changes it, sometimes he doesn't. So just for now, 1,2 product is always kinetic. Why? Because it forms the fastest, because it doesn't do any resonance. Okay, so that's how you find the kinetic product. So far, questions on that? Very good. It's always 1,2. Okay, now the thermodynamic product. What do we think that one is going to be related about? Heat? Heat? Oh, heat. I'm like, what are you guys talking about? So yeah, it is going to be related to heat. Thermodynamics has to do with heat. But more specifically, it's going to be about the most stable product. Okay. In this case, we have a double bond present. And I asked you guys this question last time. How do we know that a double bond is more stable than another? It's the more substituted. That's going to be the most stable one. So from the 1,2 and 1,4 product, which one is more substituted? It's the 1,4. That one is tri-substituted. The very first one was di-substituted. So this guy is going to be my thermal product. So questions on that? Specifically just looking at the characteristics of the molecule, that's how you find them. And yeah, sometimes your product from 1,2 can be both kinetic and thermal at the same time. Questions so far? We're good? So far, so good? Yes. No. And actually, just by looking, if you're given an energy diagram, then yes, you can tell. But, okay. No other questions on the actual mechanism. So let's see what's going to happen whenever a diagram is given to you. In this case, you are expected to know what's the kinetic and what's the thermal product. So in this case, let's look at those two aspects at the bottom. So your kinetic product, remember, it's all about the rate of the reaction. It sounds similar to the enzymes. So what do enzymes always do? They always lower the activation energy. So we're just looking for the lowest activation energy whenever we're trying to find the kinetic product in that graph. And then the thermodynamic product is not about the activation energy. It's all about potential energy. So let's start looking at our diagram. So first of all, you're going to be looking at two main areas of each of those graphs. So first of all, you're going to look at the very top. The very top, that's going to tell you your activation energy. Okay. The higher it is, the higher the activation is. The lower it is, the lower the activation is. So just by looking at that, what's going to be the kinetic product? It's gonna be A. That's the one that's the lowest. So this guy is kinetic. And then now, if we're trying to find the thermodynamic product, we're not looking at the very top. We're actually looking at the very bottom. This line in here is representing potential energy. So if we're looking for the thermal product, we're looking for the lowest in potential energy, which is which one? It's A as well.
Why I thought thermal takes the longest.
Not always. It gives you always the most stable product. The rate of the reaction is related with kinetics. Thermal doesn't do anything with that. It's not about the rate.
So what's the reason why thermal is the lowest?
It has the lowest potential energy because at the end it creates a really stable product, I think. I don't know the actual like reasoning behind it. You are most likely not going to get asked questions on that, but you are going to get questions asked on the actual diagram. You have to identify thermal and kinetic product, and sometimes you're going to get some conceptual questions. Okay, so just keep that in mind. So far, any questions on how to read that graph? Pretty simple. You're just looking at the hills at the very bottom. That's it. So far, so good. Yes. Potential energy. Actually, let me write it over here. This one is going to be P. This one, A. Okay. If we are all okay with the mechanism in the actual diagram, let's give it a try to the next two problems. And actually, for this one, I'm going to give you 5 minutes to try and figure it out on your own. So I want you to show me 1, 2, and 1 for products, and what's going to be the kinetic and thermal products. Yes.
So the 1, 2 is always going to be the kinetic,
Yes.
no matter what.
Yes. Unless your professor states otherwise. For some semesters, he said that the kinetic product was the most stable carbocation, which makes sense. It would be the fastest one, but so far he just said that 1, 2, it's the kinetic.
And the reagents for the reactions we did, it was HBr at first, so it could just be hydrogen attached to any halogen.
Yeah, so in general, it's going to be any acid. And for this case, remember, water can be both acids and bases. It always depends on what you're given in the molecule.
So how do we differentiate this reaction from like HBr addition or like how do we-
Because you have a conjugated system. That's the main difference.
So what is stuff?
Yes, Kayla.
So write down the less substituted double bond splits open to get the hydrogen, right? But in this case, that less substituted one, would it be like the top part that gets the hydrogen?
What do we think? What do we think?
If I do what I thought,
Take
it would be
5
less.
minutes. Talk with each other. Try to figure it out. 5 minutes.
Can you pull the QR code out?
Yeah, and actually, let me do it now. While you guys are solving the problem. So yeah, if you didn't scan the QR code, please do so right now.
Yeah, this is there. Yeah. This is 1, 4. Oh wait, but never mind. Wait, where is the other one? This one, where is the one?
Oh,
So what we're comparing the height.
This is blood.
Bromine.
So 2, so 3. So 1, 2. the product.
Okay, so then this is 1-4.
Yeah. 'Cause it- I did, yeah, that's what.
So this is 1-4. No, it's like 5.
Instead of
1, 2. So how many is that? So that when the hydrogen was here, no.
Yeah, this is one. No.
So the chlorine would be there. No, so it's 1, 2, 3, 4. How is this 4? Because where is it? 1, 2.
1, 2, 3, 4. 1,
Okay.
2, 3.
So you were right or? Because this
I'm gonna
is.
make it 1, 2,
1, oh, you're trying to make the 1-2 product first? This is the 1-4 product, isn't it? Right? I woke up at 8 beside my bed. With the. Dang. I feel like it's 13. Really? You never grab? The bone has. Oh, you should be like a dog.
For the first one, are there two thermodynamic products?
There's only one.
But I feel like there's three total products. Because I feel like, see that's. If that second bond.
Mhm.
That's the less substituted bond, that's where the thermodynamic product comes from, right? But there's, the chlorine could attack the top one bond part of that.
Can you draw it up?
I draw it out.
Oh, that's good.
So this, I believe, is a kinetic product.
That's the 1-4 product, yes.
And then this hydrogen, it could attack for the thermodynamic plus. I only put 1 because I feel like this is more stable than that. But it could attack, the hydrogen could, or this bond could, this part of the bond could attack the hydrogen, or this part of the bond could attack the hydrogen.
That's good too, yeah. So technically, yes, you're gonna have like multiple products, but in this case, because we're only trying to form 1-1 for product, we're only gonna focus on those.
1, 2, 1.
Yes.
Okay, so this is the main, the one that's better to fix you guys.
Yes.
Oh, okay.
Let's see.
This would also be considered a
Dynamic product, it would have it.
This one is gonna be the thermal product.
Now?
Yes, these two.
And that would be-
They're tri-substituted. And yes, technically it's more because we have lesser clearance overall, so overall it's like a perfect molecule.
Oh.
In this case, you attach the chlorine to carbon 1. In carbon 1, you always attach some sort of hydrogen. And then whatever some sort of hydrogen, then whatever halogen you have here has to go to 2 and 4. In this case, you need a hydrogen over there and a fluorine.
I think it'd be a high. Because I'm saying.
In that case, it would be 2-1 product. Because the first number represents where you attach that hydrogen.
Okay, so this is correct, right? Okay, so. So let's say you're about. That's the one carbon. 1, 2, 3, 4. So
You always start from the left side, the hinder side.
less there.
So let me say this is 1, 2, 3, 4. If you start the other way, then you're starting with the more substituted, no one, more circular.
So all of these products are complementary.
Yes,
So which is, well, we're only considering, but these two are correct. There's one.
yes, we're only focusing on 1-1 product. And I think that actually Dr. Roche showed you guys like 1, 2, 1, 4, and 1, 6 reactions. So I'm not sure if that's gonna be in your active time. He has never tested it. Yeah, I know that he did, but I'm not sure if that's gonna be on the exam. Usually it's not. I'm not sure if he just did it for funsies or it's gonna be so. Yeah.
It's with.
If it's on the quiz, then yeah, definitely. Okay, everyone. Do we find the products? No? Yeah, maybe. Okay, volunteer for the first reaction. Okay, they're volunteering you. Go for it. Okay, maybe. Do we all agree? Alior? No, why not? Show me. Go for it. How will you modify it? You can, oh, sorry about that. Okay, so we're showing the hydrogen. Mhm. Okay, so we did a little hydration shift.
I think we just counted different.
We counted different.
Yeah.
Okay. So let's walk through this problem first. And actually, first of all, did everyone number the carbons the same way that it's in there? Or do we do it differently?
How do you even know where to start?
Great question. Remember, we always start from the less substituted hydrogen. Sorry, from the less substituted double bond, from the less sterically hindered side. So that's why we're starting to come from left to right in that case. Now, let me erase this part for now. We have our numbering. Very first step, once you are able to do that, remember, that first double bond is going to be attacking that acid. So we get that hydrogen on position 1. So in this case, let's modify this a little bit.
How do we
So-
know it doesn't go to?
Because we're always trying to achieve the 1-to-1 for products. Technically, yes, it could, because it's not like Markovnikov or anti-Markovnikov.
Yeah.
So yeah, technically you can create multiple products. I know that there's even like a 1, 2, 1, 4, 1, 6 reaction. So there's a bunch of possibilities in this case, but let's, yes, we want it on position 1. There's my hydrogen from the attack. And then I still have that double bond in between carbon 3 and 4. And now I have a carbocation over here.
Why?
Because remember, once we do the attack, we're using the pi electrons in here to make the new bond, to make this bond. So that means that these 2 carbons are going to be lacking a bond. So they're not going to be that stable. So this hydrogen is always going to go to position 1. And then the other carbon, it never regained that bond. So that's why we have a positive charge over there. Okay. Now, once we have that, are we going to do any rearrangements? What do you think?
Well, we want the 1-4 position,
In this case, exactly, we want to achieve 2 main products, 1, 2, and 1, 4. So in this case, the stability of the carbocation is not going to be that concerning because if I shift it, I'm going to get different products. So in this case, I'm just going to proceed with that secondary carbocation. It's still stable. It's still in the allylic position. So it's still okay to go. Now we have that bromine minus.
Yeah.
Oh, thank you.
right?
Cl minus in there. So negative and positive, they attract each other, so that chlorine is gonna be attacking my carbocation. So at the very end, I have that hydrogen, carbon 1, 2, 3, and 4. And I have my chlorine in carbon 2. And I still have that double bond between 3 and 4. So again, because I'm connecting my hydrogen in carbon 1 and my chlorine in carbon 2, this is gonna be my 1,2 product.
Is he gonna like say name this product?
I haven't seen him ask that question before, but it would be fair game. Yeah.
So how would we do one
It should be what has a higher priority, halogens or double bonds?
double?
Double bonds. So you're gonna start from here. 1, 2, whoops, 3, 4, 5, and 6. So it should be
One methyl.
hexene in position 1, then I have chlorine in position 3. And then I have a little methyl. 1 methyl hexene. Yeah. Who's here?
Mhm.
Question? Yes. We always start with the less substituted side. And yes, you're always basically just pretty much creating the 1,2 product always. That's like the first one.
He or she did.
It's because hydrogen, let me label them. This little hydrogen, it's in carbon 1. And then in carbon 2, we have the chlorine. I'm sorry? Yes. Technically, you can do a few extra products, but again, the goal is to create 1, 2, and 1, 4. That's it. We don't care about the rest. But okay, so what am I gonna do to create the 1, 4 product? Yes. So we're gonna be doing some resonance in here. And in this case, it's in carbon 1 based on that that ranking that we did in here. We start from the less substituted side. We're not following the IUPAC way to label it, okay? Now in here, let's change this a little bit. So in this case, if we wanna shift that double bond over here, that means that my carbocation is also gonna move to the 4th position, which is what I want.
How do you know you're moving that double bond, not the other?
Because at this point, there's no other double bond. Both products always start with the same first step. They both attach the less substituted side. After that, we create that first carbocation. Because it's in position 2, I can proceed with the reaction and I get one of my main products. And then to achieve the 1 per product, I have to shift things around. So I'm gonna do a little bit of resonance in here. So the double bond is gonna move to the other side over here. I still have that hydrogen in carbon 1. I never touched it. And now I have my carbocation in carbon 4. So this is 1, 2, 3, and 4. And let's keep labeling these ones.
So wherever you move the double bond from, that's where your carbocation goes.
Yes. So now we have that chlorine minus. So again, positive and negative, they attract each other. So we attack that carbocation and we end up gaining chlorine in carbon 4. Let me redraw this little double bond over here. And then in position 1, we just have the hydrogen. And actually, let's finish color coding this. Which one? So this guy is your 1, 4 product. And again, let's label them. Okay. Questions? We're good. We followed that. Did anyone get those 2 products? Now we do. I mean, that's good, yeah.
just about reviewing.
It's a bit of review, yes.
So, remember
Yes.
what I was showing you before, where going completely, I thought like, was 100 degrees, 180 degrees from the metal group?
Yeah, you drew it out over here, I think. That would be 180 degrees.
No, I'm talking about the chlorine being, so,
No, yes. If we didn't have that chlorine in there, it would be a molecule like this, for example. Methyl group is over there, chlorine is over here.
Yeah.
They're 180 degrees apart from each other. So yes, and that technically would be the overall most stable product. But again, in this case, we're not looking for that. We're always looking for 1, 2, and 1, 4.
so would that second double bond by the method never react?
You would need something that's really, really strong. A really strong acid with probably some sort of catalyst to make it react. Okay. Okay, so we got 1, 2, 1 for products now. What about the kinetic and thermal product? What's the kinetic?
1, 2.
1, 2, beautiful. What about the thermodynamic product? 1, 4, really quickly, 1, 2. How substituted is it? Mono, di, tri, tetra?
Well, shouldn't that be the thermal product, because most of.
Let's review it. So 1, 2, we have 1, 2, 3 R groups. So this one is tri-substituted. The one at the bottom, 1, 2 R groups, di-substituted. What's better, tri or di? Tri. So in this case, the 1, 2 product, it's also the thermodynamic
So
product.
the thermal one isn't always the 1, 4.
It's not always the 1, 4. Remember, thermal is all about the stability of the double bond. Kinetic, fastest one, 1, 2. That's it, because it doesn't do resonance. Unless your professor starts mentioning the stability of a carbocation. Okay, so I'm gonna keep an eye out for that. And if we have to, we'll adjust it. But for now, 1, 2, kinetic, thermal, most stable double bond. That's it.
So more substituted.
Mm-hmm. Yes, that's why I made you guys that question last session. What makes a double bond stable?
Right.
Mm-hmm. Okay. Questions on that problem? We're good? We got it? Yes.
Why don't we run the bond?
The double bond, so we can move that carbocation to position 4, because the goal is always to create 1, 2, and 1, 4. So wherever that carbocation is, that's where I attach the halogen. Yes. Yes, unless your professor states otherwise. So yeah, I'm gonna keep an eye out for that. I don't think it's gonna change it this semester, but still, I'm gonna be careful. Kinetic is always the one that forms the fastest. The thermal, it's all about the stability of the double bond. And sometimes they're gonna be the same molecule. So yes. Kinetics is all about like the rate, the speed of the reactions. Thermal, it's all about like the stability, heat of the reaction, and all of that. That's why the 1, 2 product is more stable. That one is the tri one. The 1, 2 was the tri-substituted double bond. Therefore, it's more stable than the 1, 4, which was di-substituted. We care about the double bond. We don't care about the carbocation right now. Okay. Ready for the next one? We're all good? Volunteer for the next one. Come on, great soul. Give it a try. Go for it. Label your
So-
1, 2, 1, 4 and kinetic and thermal.
Does it matter that we have 2 hydrogens from the H2O?
No.
So
In this
what
case-
just the oxygen is gonna attack instead of that halogen? Instead of like the chlorine?
Remember, the goal is always to create something that's stable. So everything is gonna be neutral. So, oh god, my notes. It's not just gonna be the oxygen. It's gonna be an alcohol group at the very end.
First off, am I correct in my numbering? Never mind,
Not
never mind.
quite. We have extra.
I was calculated wrong.
Now we got it. Beautiful.
Aren't those double bonds both? equal stuff?
Yes, but one of them is more free on one end. So it's easier to attack it.
Which is
At the very end with the carbocation, yes.
Then if we did protonate, 308.
Mhm.
So isn't this already the 1,2 form?
No, because remember, after we do the first attack, that double bond is using those pi electrons to make that new connection between carbon 1 and hydrogen. So that means that carbon 2 right now, it's lacking electrons. So we have a positive charge.
carbon.
That's still there. Positive charge, beautiful. What happens now? So yeah, that OH minus is gonna be attacking,
Oh, the whole OH.
because if you just attach the oxygen by its own, you're gonna get a negative charge there. So it's gonna be a reactive molecule.
So if we just attach oxygen by itself, will it get?
It would get
protonated?
protonated with the solvent at the bottom, yes.
So we would still,
I'm confused. In the previous one, the less substituted double bond attack, why is the more substituted one attack?
They're both equally substituted. They're both di-substituted, but the
Oh,
difference
okay.
is that the one on the left has just hydrogens on one side. So it's more free to do that first attack.
Oh, okay. Yeah.
Mhm.
So
Beautiful.
just the H plus, or does it attack H plus? Or just water?
No. H plus is just your solvent. It's just lowering it away, the liquid around.
They just feel something, water.
Yes, it's less directly hindered on one end than the other.
So where does the H minus come from then?
H minus,
Oh, is that an H or?
it's an OH minus,
Oh, H.
because
minus,
we
sorry.
deprotonated that water in the very first step. So. Really?
yeah, and
So they're both equally substituted, they're both di-substituted, but the one on the right has all of the R groups clustered on one side. So that means that on one side, it's really, really less directly hindered. So it's really easy to attack it. And so far we do resonance, 4, beautiful.
what do you do?
So when you're referring to the thermal, is the OH supposed to be the more substituted or the double bond?
We're always looking at the double bond. Stability of double bond.
So this is the thermal.
But they're both equally substituted.
No, they're not equally substituted.
Well,
This is one R group, second versus 1, 2, I'm sorry, hold on. 1, 2, 3.
well,
Beautiful job, Sam. You got it. Okay, so did we all get the same products?
Yes.
So this guy was your 1, 2 product. And the thermal was your 1, 4 product. Time out.
hands
No,
behind your back.
I'm not rewriting my.
We're just taking a picture and
Yeah.
yeah. We love technology. Okay, any other questions on 1, 2, 1, 4? Yes. So bless you. If we were to, let's say, move the double one over here, we would be overcharging that carbon 1. Because it would have 1, 2, 3, 4, 5 connections. So we're breaking the oxide in there. Remember the basic rules of resonance. We never break the octet. We only move towards sp2 atoms and away from sp3. Those are just your basic rules. But let's erase this part.
And so also, you never.
No. Yeah, you always keep the hydrogen in position 1. Okay, there we go. Okay, any other questions, Don? Yes.
What are like other things besides H2O and HBr and HCl like that?
Usually those are the only ones, but yeah, it can be any acids.
And what do you like, let's say it was like H2SO4 or something, like what would you attach? OH also?
You would attach the conjugate base of the acid. So it would still be like HSO4 instead of H2SO4. Yes, because at the end, look at the pattern here. We start with an acid, and then at the very end, in position either 2 or 4, we're always connecting that conjugate base. So technically, yes, but I don't think you would use the H2SO4 so far. So yeah,
You would always be breaking the pi bond on a tertiary, carbon, correct? Because you can't, like, we wouldn't initiate the reaction by putting the pi bond on the 3-4 bond.
yeah.
You would start on the 1-2 bond because it's more substituted, it can handle that, the carbocation.
It's not about the carbocation.
So why does?
Because either way, the carbocation, no matter which one you attack, it's gonna end up being allylic. So if it's like primary, secondary, tertiary, it's still in the allylic position, so it's happy enough. But the reason why we do the attack on carbons, well, on the double bond between 1 and 2, is because it's less sterically hindered, so it's easier to attack the bonds in here,
Less
basically.
sterically hindered,
Yes,
which is the same for the example from before with the HCl. We started from the less sterically hindered. side.
we always start from the less sterically hindered double bond. Okay. No other questions on this reaction? We're feeling good about it? Okay, let's do a little conceptual question that is fully in condensed formula. Before we talk about the last reaction. So in this case, they're asking you for which of the following options is not a product for that specific 1,2,1,4 reaction. I have one vote for A. What do we think? No one else? Just one lonely vote for A?
So I haven't thought about this, but
I didn't even think about the question.
Okay, I'm gonna give you a few minutes to think about it.
So what, you would have to draw out the 1,3 butadiene first and see what the two products are?
No,
No?
I mean, that's one of the ways to do it, but it's gonna take you a little bit of time. And remember, the exam is always like 50 minutes, 35 questions, so.
That's great.
There's
So-
a much easier way to do it.
To do it just in condensed formula and see the main characteristics. Okay, so let's talk about this.
Two products, how could you?
Okay, let's talk about this type of question. So they're just asking for the not possible product, the thing that you're not gonna form. So let's think about how the actual products would look like. What's the main characteristic of the 1, 2, and 1, 4 products? What is it composed of?
CH3 and CH2 connecting to the pi bond,
So yes, at the end, how many double bonds do we end up with?
1 pi bond, and then 1.
Exactly.
halogen, whatever.
That's the main thing. In the structure, we only need to have 1 pi bond, 1 double bond, and whatever halogen you were given. In this case, it would be chlorine. So if we see 2 double bonds, that is not gonna be a product. And in this case, option A, exactly, option A is the one showing 2 double bonds.
Where do you see this?
They are over here.
you hear CH2, you're missing an H, so therefore there's a pi bond.
And since it's.
Remember,
It's terminal.
Hydrogen deficiency.
One
So
double bond.
CH means they have a triple bond?
CH, yes, a terminal triple bond in that case. Okay, so again, you didn't have to do the actual like full reaction. As long as you know like how the basic products are gonna look like, you should be good to figure it out. It's just always go back to the basics. Whenever you get confused with a question, simplify it, go back to the basics.
What are 3 possible products that are negative 2?
There are only 2 products that we're trying to achieve for the 1,2 and 1,4 reaction. But technically, yes, we have a few options. Yes. Maybe I drew it wrong. Probably. We have 1, 2, 3, and 4. Yeah, I have 1 extra carbon. So let's just disregard that one. Let me erase this whole thing actually. Okay, we have 1, 2. 2 has the chlorine. So yeah, I should have them over there. Yeah, there we go. 4 carbons, chlorine in the middle, conjugated, we're good.
Could you draw the 1,3-butadiene?
I think it's the reaction that we did first. Is it? Nope, we did not. It's gonna be with HCl. So that means that on 1, 3. It's that one. And then the 2 products should be. Position 1, 2, 4. There we go. Those will be the 2 possible products. Okay, any other questions on 1, 2, 1, 4?
So
Yes.
the double bond in the second product, why does it start at carbon 2?
The double bond in the second product.
Like in the 1,4?
Because I did resonance. Because technically the intermediate was this little guy. Carbocation over there. This is 1, 2, 3, and 4. I'm gonna shift it over here. So I can get that carbocation in position 4. Okay. No other questions? We're good? We're good.
Halogen ends up on most of the part. That's how the reaction.
Yes.
Sorry, one more question. So for like these types of questions, we really only need to know that check for the one that has 2 double bonds.
Yeah. As long as you know how a basic product, like the general characteristics of it is, how is it gonna be, you should be good to figure it out. Base characteristics, some sort of halogen, double bond. That's it. Only 1 double bond.
So there's not gonna be 4 products with 1 double bond and ask us which one is the product.
He might ask you for the actual product, yes. That would be a fair game too.
Incomplete.
So same type of question, but in this case, it would be like, which one is a possible product? So yeah. Okay, we have 5 minutes, so let's briefly start talking about the next and final reaction of this chapter. Let's just start introducing it. Why not? I can do it. Okay, and actually, I'm excited for this one because it's my favorite reaction. So it's my favorite reaction. Okay, so diasolder. So this reaction is going to be the one that's going to be able to create cyclic structures and especially bicyclic structures. That's why I love it. So in this case, you're going to have 2 main reagents. We always have the same basic ones, nucleophile and electrophile. But more specifically, this time they're going to be called a diene, a dienophile. And then the main catalyst that you need for this reaction is heat, which is just represented by that little triangle that you're seeing here. So that's heat, and that's it. That's what's going to be able to promote that reaction. Now, let's talk about our nucleophile, which in this case is actually going to be our diene. So let me write it in here. This is your nucleophile. And then your dienophile is going to be considered the electrophile. Now, this is going to be a reaction that's gonna happen in one single step. So everything is gonna happen in the same movement, but technically we're gonna have 3 arrows to show. So in this case, let's start with the little diene. Di means 2. In means double bond. So which molecule do we think is gonna be the diene, left or right? Left. Which means that the little dienophile, it's the other one. Okay. So,
But the one on the right isn't a dye.
no, it's not a diene.
Because it has dye.
It's conjugated, yes, but it's not a diene. So yeah,
What is-
either way. Okay, so this reaction, very simple, really cute. Diene to dienophile, that's the very first attack. We only have 3 main arrows. So, what? Don't worry. Okay, so diene to dienophile. We do that first attack. We do that first attack. Nucleophile to electrophile. Whenever we do a nucleophilic attack, we always make a new connection. So let's start drawing this over here. Now, next thing, I want to keep connecting the both molecules at the same time. So that means that I'm going to be attacking back the diene, and it's still going to be a nucleophilic attack in a way. We're still making a new bond in there. And then to adjust everything, the pi electrons have to shift in the middle so we don't break the octet. So again, this was 1, this is 2, this is 3. They're all happening simultaneously at the same time. So in this case, this bond and this bond are the new connections that we did. Because the main diene is over here. It's still in here. And then the dienophile,
File attack first. File.
Well, it all happens.
so yes, it does make more sense that way, but in the actual mechanism, the one that acts as the nucleophile is the diene. Go for your reason.
I'm confused.
Again, he's not gonna be asking about the mechanism, so do it whatever way works best for you.
Is there any way you could explain those 3 arrows one more time?
So yeah, remember, very first arrow, that's gonna be the first connection that we make between diene and dienophile. It's a nucleophilic attack, so we start making a new bond, the one in red. That's representing the first arrow. Second arrow, to keep connecting those 2 molecules, the dienophile has to attack back the diene. So that's the second nucleophilic attack, second connection we make. And then the third arrow is so we don't break the octet, so we shift the electrons up. So technically the third arrow is kind of like resonance in a way.
Do we need to know the mechanism?
No, I just love to show it.
Could he ask us like conceptual questions on the mechanism?
On the mechanism, probably not, but he might ask you for which molecule acted as the nucleophile. That's why I try to show it this way, even though it makes, visually, it makes more sense for the dienophile to do the attack. But again, I'm just trying for you guys to remember diene. It's actually the nucleophile. Dienophile, electrophile. The actual movement of the arrows, you can do it either way.
So question.
Yes.
What is the COH? Is that also a done?
The COH, what kind of functional group is it gonna be? Come on. Which one? An alcohol? Whenever we see carbon and oxygen right next to each other, that means that we have some sort of carbonyl group. So if this is the main area of the carbonyl group and we just have an extra hydrogen, this is a little aldehyde.
Oh. Yeah.
Do we see it? We not see it? So remember, in condensed formula, usually whenever we're trying to draw any of the carbonyl groups, we're just gonna pair the carbon and oxygen together. That's representing the double bond.
So that's
Over
an
here.
electron.
So.
It's
should
an
that
electron
C-
withdrawing
should
group.
that C not be there for it to be an aldehyde?
Because you think that this N represents a carbon?
Yeah.
It doesn't represent a carbon. The bond from the double bond is directly connected to this carbon over here. So the little dot, it doesn't represent any carbons. It's just showing the bond.
Tangled, pregnant,
Yes.
So the diene the nucleophile is always gonna have two double bonds, that's how we know it's a nucleophile.
Yes.
But will the dienophile ever have two double bonds?
Technically, this one has two double bonds because it looks like, let me draw it up for you.
Oh, cause the COH is,
It looks like this.
so how will we know which one?
The diene needs to have two double bonds that are just carbon to carbon, pure carbon and carbon. And you don't need any sort of carbonyl groups adjacent to it, but we're gonna talk more about it on Monday, actually.
To differentiate. between
Mhm.
them?
So yeah, so overall, it's not such a bad reaction. It's really cute. Everything happens in one single step. I do call it a reaction here. So yeah, there's a few practice problems like on this handout, so give it a try. Let's see what happens.
And then could we, like, instead of using a COH, you could use any electron drawing group,
Mhm.
like such as.
Any carbonyl groups, a cyano group, for example, but I'm gonna give you a specific list of electron withdrawn and donating groups that you might encounter.
And when he does extra credit in class, does he actually like go through each one and write down the name of the one who did it, or does he just boost everyone at that?
I think he just like collects the pile of students that are there and just based on the actual like name, he just inputs like whatever extra credit he wanted to give you. So if it was 5 points, looks like your name, add 5 points, that's it.
But
I don't think he checks for accuracy.
But does he actually check the name?
Yeah.